Okay, this question will be about conservation of mechanical energy. So we have a roller coaster that has an initial height of 12 meters. It is released with only one car, and that has a mass of 250 kilograms. Its initial velocity is 0. It says it's from rest at the top of the first hill, and it proceeds to fall down to a height of 0 meters, and then over a second hill, which has a height of 7 meters, and finally moves down and then over a third hill where it moves at a speed of 5.4 meters per second and then continues on. So the first question asks us, what type of energy does it possess at the top of the hill? Well, the velocity is 0, therefore the total energy it has is only gravitational potential energy. So here's my total mechanical energy. That means that this is the only term that there's any value to, because here velocity is equal to 0, so there will be no energy from kinetic energy. It will be all gravitational potential energy. Number 2 asks us to calculate it. Well, that would be the mass of the cart times acceleration due to gravity, but it's only a scalar in this case, times the height of the first hill. So I'll call that h max in this case. So if I wanted to calculate that, I could calculate it, and that would equal 250 kilograms times 9.8 meters per second squared times 12 meters. Put that in a calculator and you get 29,400 joules. If I had to round that to two significant figures, it would be 29,000 joules. So since I know this number, and I'm just going to put this here, then I know the total energy anywhere on this roller coaster, assuming that we're ignoring friction. So I've grouped the questions together. These next 3 questions are grouped together, 3, 4, 5, because these are the different things you need to think about, and hopefully by the end of this lesson you'll be able to see it's really one idea, but you need to make a couple steps to get there. Okay? So with the second group of questions, 3, 4, 5, I'm just going to cover up that one right there so that you can see the picture and the questions at the same time. 3, 4, 5 asks us about the bottom of the first hill. So I'm right here. What type of energy does the car possess at the bottom of the first hill? Well, it has gravitational potential energy, has kinetic energy, but height is 0. So there will be no gravitational potential energy. All the total energy will be in the form of kinetic energy. Just this one right here. That is it. Do I know the total energy? Yes, I do know the total energy. It equals 29,000 joules, but if I'm doing calculations, I need to use the unrounded value. So, here we go. 29,400 joules, and here I can solve for V because it is my only unknown. I know what the mass is. So put in the values I know. Okay, and now you are going to use your math skills and solve for that. So I would take 250, divide that by 2. You're going to get 125. And then we will rearrange this equation, dividing both sides by 125, and then square rooting. Because a square root is the opposite function of square. And you get square root, and I get 15.336. And if I go ahead and work out my units, a joule per kilogram ends up being a meter squared per second squared. You can work that out. So that if I square root it, it becomes meter per second, and my speed at the bottom of the hill will be approximately 15 meters per second. Okay. So I'm going to go on and do the last group of questions. So let's go over and just go over 3, 4, 5. Number 3 asks, what type of energy does the car possess at the bottom of the first hill? Well, it only possesses kinetic energy. Gravitational potential energy is equal to 0 because the height is 0. How much total mechanical energy does the car have at the bottom of the first hill? It has the same amount that it had at the very top. That's the whole point of conservation of energy. It's not going anywhere, it's just being converted into different types. Make up a relationship between the answers to 3 and 4. Well, the total energy is equal to 1/2 mv squared. This V is at the bottom of that first hill, right here. This is where I'm answering 3, 4, and 5. And this is the equation that you're solving. And that's what I did here. Okay? So let's go through that same thought process with 6, 7, and 8. So 6, 7, and 8 ask us about the top of this second hill. What type of energy does the car have at the top of the second hill? Well, at the top of the second hill, it has gravitational potential energy and it has kinetic energy. Well, how much does it have? Well, it has m, g, h, and I know that. I know what the height is. It's 7 meters. Does it have kinetic energy? Well, how's it going to get over the hill if it doesn't? And if it's not, all the energy isn't in the gravitational potential energy, then there must be some kinetic energy left over. Over here on this side, this is the last one, or number 7. How much total energy does it have? It has the same as it did before. I'm going to put it in this time, though, as mgh max and show you that the mass is irrelevant in this question, and you can solve this a little bit different ways. So right here, this number is that 29,400, but I'm going to put it in as this and show you that mass is in every term so you can divide it out. It reduces the size of your numbers and makes it an easier question to solve. So that's what I'm solving for, the speed over the second hill. This is the height of the second hill. This is the maximum height. This is the height of the first hill. Notice that everything on this side of the equation has to do with the top of this second hill. This side is the top of the first hill. All the information on this side of the equation is at one location, and all the information on this side is at another. You cannot mix the two up. So here we go. We have 9.8 meters per second squared times 12 meters equals 9.8 meters per second squared times 7 meters plus 1/2 v squared. Now this probably isn't how I would solve it, because I like to solve for the variables, but a bunch of you are getting mixed up with all your variables, so I'm going to go ahead and try it this way. It's different than how I did it in class. So 9.8 times 12 is 106, and that's going to be meters squared per second squared. I'm leaving in my units to show you how important they are when it comes to keeping track to see if you've rearranged things correctly. And you'll notice that I have meters squared per second squared, meters squared per second squared. These are the same units. Think about if you squared the units of speed. You'd also have meters squared per second squared. That means that all these terms have the same dimension. So I'm going to go ahead and subtract 68.6 on both sides. And I get exactly 49. Okay. and there's my 1/2 v squared. That becomes 49. Then I am going to multiply by 2, multiply by 2. That's why I chose to multiply by 2, because I wanted to get